Good afternoon, ladies and gentlemen. My name is Tomasz SMOLENSKI from Atachimamoglu Group at ETH Zurich. And first of all, I would like to thank the organizers for providing me with the opportunity to give this talk. It will not be about polaritons, but rather about our recent observation of a Wigner crystal of electrons in a monolayer semiconductor. So this work was done in collaboration with theoreticians from Eugene Daimler Group from Harvard University, as well as with Kenji Watanabe and Takeshi Taniguchi, who provided us with HBN crystals. So in the beginning, just to give you a very brief introduction, let me remind you some of the most important properties of electron systems in two-dimensional materials. So as you all know, in case of highly doped semiconductors or metals, the electrons form a Fermi liquid state and may be described as essentially non-interacting quasi-particles that obey Fermi-Dirac statistics. And this is a consequence of the fact that at large electron densities, the kinetic energy of the system greatly exceeds the Coulomb repulsion. However, this may be modified by reducing the electron density, which allows to increase the relative strength of the Coulomb interaction that scales slower with density compared to the kinetic energy. And as a result, at sufficiently low densities, it is actually possible, so the Coulomb energy can be sufficiently strong to compensate for kinetic energy cost of localizing the electrons and thereby allow them to spontaneously break the translation symmetry and form a quantum crystal, as it was predicted 100 years ago by Eugene Wigner. And according to some more recent quantum Monte Carlo simulations, the actual ratio of the two energy scales, that is termed RS parameter, which is needed for such a Wigner crystal to emerge, must exceed roughly a factor of 30. And this turns out actually to be a very stringent condition that is almost impossible to be met in conventional semiconductors, as for example, in case of gallium arsenide quantum wells under typical experimental conditions, this RS is of the order of unity. And further increase of this value would require, to reduce the density to a level at which the disorder starts to play a dominant role. So this is actually why most of the previous experimental studies of Wigner crystals have been focused on two-dimensional materials that are subject to a strong out-of-plane magnetic field, which breaks the electronic band into Landau levels and thereby quenches the kinetic energy. And in such a case, the electron-electron interaction entirely governs the properties of the ground state of the electron system, which means that the system will always crystallize at sufficiently low density. However, even in such a case, the electrons, instead of crystallizing, may in principle, for example, capture some magnetic flux quanta, form a composite fermions, and which gives rise to emergence of fractional quantum Hall states. And for example, the competition between those states and Wigner crystal leads to oscillations of magnetotransport that are observed in gallium arsenide quantum wells. So the resistance, as you can see, goes down each time the system enters fractional filling or integer one, whereas it essentially diverges when the electrons form a Wigner crystal, as the system there becomes electrically insulating because Wigner crystal is pinned by the disorder. And disorder pinning was also, for example, evidenced by the observation of this high frequency resonance that originates from oscillations of the Wigner crystal around the disorder potential minimum that disappear when the Wigner crystal is being melted upon increase of the temperature. So even though these kind of experiments provided, as you see, very useful insight into macroscopic properties of Wigner crystals, they actually have failed to unequivocally demonstrate the existence of a long-range charge order. And some new avenues for this kind of research emerged with the recent advent of, monolayers of transition metallical cogenites, which allow to explore a fundamentally different regime that was inaccessible for conventional materials. And this is actually due to both very large electron effective mass and also reduced dielectric screening that, together with relatively limited disorder, and because of this, the RS values that can be reached are actually more than order of magnitude larger compared to gallium arsenide at the same density, and this thing, together with a limited disorder, holds a real promise for observing a Wigner crystallization at zero magnetic field. But this striking contrast to conventional materials is also present upon application of the field. So in this case, the Coulomb interaction between the electrons that are separated by magnetic length turns out actually to be much stronger than the cyclotron energy at moderate magnetic fields. And this leads to a very strong Landau level mixing that was previously theoretically predicted to promote the Wigner crystal by lowering its energy compared to the fractional states. And this opens a possibility for observing a Wigner crystal at those fractional fillings or even at integer ones. And during my today's talk, I will show you that this is indeed possible, and I will present the data that demonstrated that the electrons in TMD monolayer form a Wigner crystal even at zero magnetic field. So these findings were revealed by our magnetospectroscopy experiments that were carried out on 2 different devices, out of which I will focus here on this device that similarly as the other one consisted of a charged tunable molybdenite monolayer that was electrically contacted with a few layer graphene flake. Then it was encapsulated between 2 layers of hexagonal boron nitride, and finally sandwiched between other 2 few layer graphene flakes that served as top and back gates, out of which we only utilize the top gate here to tune the electron density in the present experiments. So all of these flakes were mechanically exfoliated from bulk crystals. Then the stack was assembled by means of a dry transfer method. Then it was released on sapphire substrate, and finally gold electrodes were patterned and assembled by means of electron beam lithography, followed by metal evaporation. So for the experiments, this device was loaded into a dilution refrigerator that allowed us to reach a base temperature of about 80 millikelvin and featured a fiber-based optical access that allowed us to perform resonant reflection experiments with circular polarization resolution and at magnetic fields up to 16 Tesla. So here you can see an example zero field gate voltage evolution of the reflectance contrast spectrum obtained for our device. So as you can see, at negative voltages, when the device is devoid of any free electrons, its spectrum features just one resonance simply related to the bare exciton. And then when the gate is ramped upwards, and as the electrons start to be injected to the monolayer, they start to dynamically screen the excitons, which lead to their dressing into so-called Fermi polarons. And the prominent signature of this crossover is the emergence of a second lower energy resonance that is due to attractive Fermi polaron, and it appears in the spectrum exactly at the onset of filling the band with electrons. And at the same time, the exciton transition smoothly transforms into repulsive polaron, and then blue shifts, broadens, and finally fades away from the spectrum. So for our further analysis of Wigner crystal properties, it is actually essential to precisely determine the electron density based on the gate voltage value. So in most of the previous studies of similar samples, this task is typically accomplished by modeling a device with a parallel plate capacitor. However, this approach is often fraught with systematic error due to sizable uncertainty of HB and the electric constant, and to some extent also its thickness. So in order to avoid these difficulties, in our study we actually utilized a different, more accurate approach in which we determine the density based on the observation of Shubnikov-Tikhas oscillations of the exciton transition at high magnetic field. So as we demonstrated in our previous work, under such conditions, the exciton resonance gets narrower each time the system enters integer quantum Hall state. And by tracing this minima of the line width, we can then determine gate voltages corresponding to integer filling factors, which form this Landau level fan chart. And then knowing that in our system, Landau levels are fully spin and valley polarized, this allows us to establish a link between the density and the voltage, and allow us to extract precisely the value of this density that is shown here on this right axis. So From now on, I would like to focus here on this low density region in the spectral vicinity of the exciton transition, where we want to observe Wigner crystal signatures. And in search of those signatures, we actually use our novel technique of detecting long-distance charge order that is based on the observation of the corresponding modification of the exciton dispersion. So in a simplest undoped case, such a dispersion in a TMV monolayer has this parabolic shape with a curvature simply determined by the exciton mass. And then when the system gets doped with electrons in a Fermi liquid state, the dispersion remains essentially almost unchanged, except for the fact that it gets slightly blue shifted owing to a combined effect of phase space filling and bandgap renormalization. However, this picture changes qualitatively when the electrons form a Wigner crystal. As in this case, the exciton-electron interaction ensures that the exciton experiences a periodic potential, which allows it to get umklapp, or in other words, Bragg scattered of the Wigner crystal, in exactly similar way as the electromagnetic wave can get Bragg scattered when it encounters a regular crystal. So for both of these scattering processes to be effective, either the light momentum, or in our case, the exciton momentum, must match the reciprocal lattice vector of the lattice, which I denote here as Kw. So this means that the exciton of this momentum, which is optically inactive, will get folded back to the light cone, where it will start to hybridize with the zero momentum bright exciton state, and thereby acquire some finite oscillator strength, which will lead to emergence of a new, weaker optical transition in the spectrum. So importantly, the splitting between this transition and the main one in the limit of weak exciton-electron interactions, which is actually relevant in our case, is simply given by the kinetic energy of the exciton at this momentum Kw, which means that this splitting is going to increase linearly with increasing electron density, while the Wigner lattice constant is getting reduced upon injection of extra electrons to the system. And now turning back to the experimental data, you can see that this peak is maybe not directly visible in the bare reflection data, but it becomes prominent after taking a derivative with respect to gate voltage, as you can see here. So this peak indeed blue shifts much more abruptly with the density compared to the main transition, and it also becomes indiscernible at around a density of 2 or 3 times 10 to the 11 electrons per centimeter squared. But most importantly, the splitting between this peak and the main peak that is extracted from our data follows precisely this expected linear dependence on the density, and also it extrapolates to 0 in the zero density limit. So the slope of this dependence also corresponds to exciton mass that within the experimental uncertainty actually agrees with the value that was provided by prior transponded ARPAS measurements for mold diselenite monolayers, which actually provides a strong confirmation that our identification of this transition as originating from the umklapp scattering of Wigner crystal is correct. So further support of this conclusion is also provided by independent set of our experiments that were carried out on a bilayer sample consisting of 2 moly diselenite monolayers that were separated by HBN monolayer. So importantly, in this case, these moly-selenite flakes were twisted with respect to each other by about 1 degree, which gave rise to a Moire superlattice and the corresponding Moire potential for the electrons. So now if you imagine that we dope one of the layers in the system, say the top one, these injected electrons will, occupy subsequent Moire unit cells. And at some point when the density is tuned to a level at which there is 1 electron per each Moire unit cell, then the mutual Coulomb repulsion between the electrons will actually suppress the dual occupancy of any lattice site, resulting in a formation of incompressible Mott insulating state. So in such a state, obviously there is periodic charge order, so it should create a periodic potential for the exciton, leading to emergence of the umklapp peak, which is actually indeed what we observe here, this Umklapp peak lights up in the experimental data. And importantly, now this Umklapp peak is actually visible only in a very narrow density range around the unity filling of the Moire band, which is simply due to the fact that that when the density is tuned away, the mod state melts and the system undergoes a phase transition to a not ordered metallic state. And yet another important difference to a case of Wigner crystal in a monolayer semiconductor is that now this Umklapp energy is not tunable with the gate voltage, as here the electrons do not spontaneously break the translation symmetry, but instead their lattice geometry is fully determined by Moire periodicity. So in spite of the existence of these differences, the fact that we observe those Umklapp signatures in both of these experiments actually strongly confirms the interpretation of their origin, that they herald the presence of a charge order in a system. So from now, I would like to focus back on a case of Wigner crystal in a monolayer semiconductor. And I would like to explore a bit more properties of this Wigner crystal, starting from the analysis of its response to temperature change, which is revealed by these two maps that show you the gate voltage evolution of differentiated reflectance contrast spectra taken at 80 millikelvin and at 4 Kelvin. So as you can see, the Umklapp peak becomes much less intense upon rising the temperature, in contrast to the case of the main transition that remains virtually not affected. And this finding actually reveals that even though the increase of the temperature to 4K is not sufficient to melt the Wigner crystal, it is actually strong enough to increase the thermal fluctuations of the electrons around the Wigner crystal lattice sites, which then effectively decreases the modulation depth of the potential that is experienced by the exciton, and thereby reduces the corresponding amplitude of the Umklapp scattering. So yet another possible way to modify the spatial profile of the electrons forming a Wigner crystal is to apply external magnetic field that partially quenches kinetic energy and thereby, should enhance the stability of the Wigner crystal. And this should give rise to more pronounced Umklapp signatures, which is indeed the case, as you can see here for 6 Tesla in sigma minus and sigma plus polarizations. So even though in both cases, the Umklapp peaks are stronger than compared to the zero field case, the peak in the sigma minus polarization has larger intensity, as you can see. At the same time, though, the energies of those peaks are almost identical, in contrast to the case of the main exciton transition that are sizably split between the two polarizations owing to a strong Wally-Zeeman effect. And this striking difference in the splitting of the two resonances actually is due to strong electron-hole exchange interaction that lifts the Wally degeneracy of non-zero momentum excitons by mixing them and thereby splitting into two linearly polarized branches like this longitudinal and transverse that are separated by exchange energy that is proportional to the k vector, to the momentum. And this splitting turns out to be strong enough that it almost completely suppresses the Wally-Zeeman effect for finite momentum excitons, and thereby it quenches the magnetic response of the Umklapp state. And this actually means that the splitting between the Umklapp and the main transition is now different in the two polarizations. And even though both of these splittings, they increase linearly with the density with the same slope as in the case of the zero field, now they do not extrapolate to zero in the zero density limit, but instead they extrapolate to a value that is determined by the Wally-Zeeman splitting of the main peak. And also, the fact that now the separation between Umklapp and the main transition is smaller in sigma minus polarization, it also entails stronger hybridization of the Umklapp peak with the main exciton in this polarization, which also explains why here it is stronger. So I would like to stress that all of these theoretical considerations that I presented, they were actually confirmed by the full numerical calculations of the exciton band structure in our system that were performed upon assumption of contact-like interaction between the exciton and the carriers that was actually modeled as spatially dependent Hartree shift of the exciton energy. So now, knowing that the umklapp is exhibiting vanishingly small magnetic response, while the main exciton is exhibiting strong Wallis-Zeeman splitting, we can actually expect that by increasing magnetic field, we can shift the Zeeman split branches of the main transition such that the umklapp will actually emerge in between of them, as shown in this scheme. So in such a situation, if we increase the doping density, we should shift the umklapp state upwards and thereby bring it to a coincidence with sigma minus resonance of the main exciton, which should lead to emergence of an anti-crossing between the two states, which is precisely what we observe at 14 Tesla in sigma minus polarization, as you can see here. So kind of remarkably, in such a under such conditions, the hybridization between the umklapp and the main exciton state turns out to be strong enough to allow for the observation of the umklapp even in the bare reflection data, as you can see in this left map. So at the same time, no anti-crossing is observed in sigma plus polarization, as here the umklapp is actually much weaker, owing to its much larger detuning from the main exciton transition. So coming back to this anti-crossing, it is actually very essential to note the striking asymmetry of the intensities of the two transitions that are involved in this anti-crossing. So as you can see, at low densities, both umklapp and the main peak are visible, whereas at higher densities, the umklapp becomes rather indiscernible. And this striking disappearance of this peak from the spectrum may actually suggest that we melt the Wigner crystal by increasing the density and thereby reducing the relative interaction strength. However, this somehow remains in apparent contradiction with the fact that it may seem that this peak reappears in the spectrum around integer filling somewhere here. So in order to address those questions, we performed the Hartree-Fock calculations of the electron system that allowed us to obtain a tentative phase diagram that is presented here as a function of the filling factor of the Landau level in this vertical axis and the strength of Landau level mixing in the horizontal axis. That is actually inversely proportional to the square root of magnetic field. So as you can see, at low magnetic fields, when the Landau level mixing is strong, the Wigner crystal is expected to be the only stable phase, which actually explains why at 6 Tesla we observe umklapp peak in a broad range of filling factors, including the filling of unity. However, when the magnetic field is increased and the corresponding Landau level mixing strength is going down, the Wigner crystal is now expected to melt upon increasing the electron density or the filling factor and undergo a phase transition to integer quantum Hall liquid. That is also expected to coexist with a kind of exotic phase of quasi-particle Wigner crystal of either excess electrons or excess holes for filling factors larger and lower than one, which is marked here by these red and blue regions. So importantly, the umklapp scattering of this quasi-particle Wigner crystals is expected to occur at very small energies, which is unlikely to be observed in the experiment, which actually provides a tentative answer as to why the umklapp peak disappears at 14 Tesla from our data around a filling factor of half or 0.6, 0.7. But now it is still important to answer why it seems to reappear around this integer filling. And in order to address this issue, we performed a calculation of magnetoplasmon dispersion in the case of integer quantum Hall liquid. And as you can see, this dispersion features a very pronounced minimum around the momentum that roughly corresponds to the lattice inverse reciprocal lattice wave vector of the Wigner crystal at the same conditions. And now the magnetoroton excitations that are associated with this minimum can dress the exciton that interacts with integer quantum Hall liquid, and this gives rise to emergence of the high energy peak that it is shown in exciton spectral function that is actually much broader than the umklapp peak, but it may be actually responsible for this emergence of this peak in our data at 14 Tesla. So with this, I would like to conclude my talk. So I've shown you that the electrons in a TMD monolayer form a Wigner crystal at low densities. And this finding was revealed with the use of our new technique of detecting long-range charge order that is based on the observation of a new Bragg or Umklapp transition that emerges due to the scattering of the exciton of the periodic crystalline lattice of charges. And our result actually demonstrate that TMD monolayers allow to explore the strongly correlated electron systems in the parameter space that was so far uncharted. So this includes also a possibility of investigation of a phase transition between quantum liquid and quantum solid with a multitude of exotic phases like bubble or stripes that are expected theoretically to emerge in between. So also yet another thing is that the Umklapp scattering spectroscopy may turn out to be a sufficiently precise tool to allow to discover, for example, spin phases that appear on top of a Wigner crystal state, which may give rise to some fine structure of this Umklapp peak that may be in principle observable in higher quality samples. So with this message, I would like to thank you for your attention.
Thank you very much, Tomasz. The talk is now open for questions or comments. So while people think, maybe I can start. Are there other alternative ways to evidence that you've seen a Wigner crystal, which is not relying on this Umklapp peak?
So as you see, it is very difficult to directly probe it. So actually, in the case of extended systems like two-dimensional materials, there was virtually no direct experimental evidence. Always, this evidence was relying on the behavior of some average quantity like resistance or some resonance in high frequencies. So actually, observation of a Bragg scattering is the most direct way that we were evidencing the crystal formation, even in the times where we didn't use any electron microscopes. So in this sense, actually, we believe that our technique is the most direct way that exists.
Indeed. Okay, so question starts to come. We've got one from Guillaume Malpêche.
Yes, so thank you for the very nice talk. In fact, well, I would say, so in principle, you have this polaron which forms because you have this exciton surrounded by electrons. Mm-hmm. And then on the other hand, there is this picture that these electrons, they do form a lattice on which this exciton scatter, which gives this Umklapp peak. Mm-hmm. And it seems that you see both things together, which is a bit, okay, I would not say contradictory, but it gives a feeling that you have together this Wigner crystal and still a sea of electrons which are surrounding this exciton in order to modify, okay, to show this dependence that you see, dependence of the exciton energy versus voltage. So how can it be reconciliated somehow?
So you see that the fact that this attractive polaron that most likely you are referring to is not basically very directly visible at these low densities at which we observe this Umklapp peak. So this density range ends somewhere here, and the polaron is actually emerging there. So it is a question whether this is a true polaron or maybe there are some puddles in our optical spot at which we observe some trion-like excitations that give rise to this. So it may be that we do not have a full Wigner crystal in the whole spot, but there are some polycrystalline puddles, and then the polaron appears from other puddles. But certainly it is very weak at these densities where we observe a Wigner crystal.
Okay, then we have a question from Valérie Kozin.
Hello, excuse me, I have a very naive question. Is it correct that if we add very little electrons to the conduction band and freeze the whole crystal down to very, very low temperatures, we will for sure get a Wigner crystal phase?
So in case of the system in which is subjected to magnetic field, this is true because this means that the kinetic energy is basically frozen. But in case of the ones, so in general, it would have been also true in zero magnetic field case, but then you always fight at some point disorder. Yes, if you reduce the density, at some point you will arrive in a situation where the electrons will form isolating state, but not due to the fact that they form a Wigner crystal, but actually they will form a randomly ordered state that is not not a long-range charge order. And this is the thing that in this case, we believe that we will not observe an umklapp scattering because this should emerge only when the exciton experiences a periodic potential.
Okay.
But if you don't want to study this umklapp scattering, just like from the fundamental point of view, if we don't have a magnetic field and if we froze down the crystal to a very low temperature and we added very little electrons to the conduction band and we don't have a disorder at all, we have like an ideal system, will they eventually at very, very low temperature form a crystal?
Yeah, if you don't have disorder, they should form a Wigner crystal.
Okay.
But the thing is that at some point you start to fight the disorder. And the whole idea about using TMDs instead of gallium arsenide is that you can actually get a strongly interacting regime at larger densities at which the disorder is not as important as it was in conventional materials.
Thank you very much.
Okay, thank you. We have another question from Thierry Guillet.
Thank you. My question is also about the length scale of the order. Can you estimate how many periods the Wigner crystal is coherent? And in other words, if it would be a liquid with just a single peak, two-particle correlation with a clear peak at a given distance, would you expect also some kind of umklapp signature?
You mean the clear peak at the given distance?
In a liquid where you have a two-particle correlation function with a peak.
Yes. So basically, this is what we also evidence in these calculations of magnetoplasmon. When the Wigner crystal melts, it is not that this umklapp peak will suddenly disappear, but actually, so at some point we will enter the liquid state in which this magnetoplasmon dispersion is a bit softer. So there will be still some high energy peak, or even in the case of Fermi liquid state. But what we also evidence is that when especially at zero magnetic field, this peak is expected to occur at a very different energy compared to this umklapp peak that we observe and that matches with the exciton mass. So it means that actually it is very unlikely that this is not a Wigner crystal, at least in zero magnetic field. At high magnetic fields and higher densities, you are right that especially, for example, here this signature may be due to Fermi liquid.
Okay, and to conclude, your co-author would like to say something. Atachi Mamoglu.
Yeah, so thank you. So I wanted to follow up on Tomasz's response to Guillaume's question. So basically the picture regarding attractive polaron formation is this, that the formation of the Wigner crystal modifies the low energy, low momentum excitations of the electron system. Whereas to form an attractive polaron, there are virtual excitations of the electrons all the way up to momenta of 1 over the trion Bohr radius. And as such, the modifications at the low momenta is hardly making any difference in the attractive polaron spectrum or the attractive polaron feature. So if we were to tune down the trion binding energy, then this would become visible. Or if you were to really make a very small Wigner crystal, if it were possible with the very small separation, then one would start to see the modification of the attractive polarons.
Okay, thank you very much. We are doing very badly with time, so